structure. But where does such extreme cold come from? The fact is that the Boomerang Nebula is actually a protoplanetary nebula. It is a dying star that ejects its outer layer of gas at incredible speed. The gas flies out at a speed of about 600,000 kilometers per hour, which is 150 times faster than the speed of sound on Earth. When gas expands at such a frantic speed, it cools quickly. This is the same principle that is used in your refrigerator, only on a cosmic scale. The gas expands so quickly that it doesn't have time to absorb heat from the surrounding space, and its temperature drops to record low values. This process is called adiabatic expansion. The central star of the Boomerang Nebula has already exhausted its nuclear fuel and is shedding its outer layers, creating this impressive cold shell. Scientists believe that this process began relatively recently by cosmic standards, approximately 1,500 years ago. The star has ejected a mass approximately equal to the mass of our Sun over the last few thousand years. Interestingly, such an extremely low temperature makes the Boomerang Nebula a unique laboratory for studying the behavior of matter under extreme conditions. In such cold, matter behaves completely differently than we're used to observing. Molecules move extremely slowly, and some quantum effects become more noticeable. Astronomers have discovered a large amount of carbon dioxide molecules in the Boomerang Nebula, which is unusual for such objects. This indicates complex chemical processes occurring even at such a low temperature. Water molecules in the form of ice and other complex organic compounds have also been found there. The temperature of the Boomerang Nebula was measured using radio telescopes, including the ALMA telescope in Chile, which is one of the most powerful tools for studying cold objects in space. Scientists analyzed the radiation of carbon monoxide molecules, which allowed them to accurately determine the temperature of this cosmic refrigerator. It is interesting to compare the Boomerang Nebula with other cold places in the universe. The temperature of the cosmic microwave background, the residual radiation from the Big Bang, is minus 270.45 degrees Celsius. This is the basic temperature of space that prevails everywhere where there are no heat sources. But the Boomerang Nebula is colder even than this relic radiation. On Earth, we will never encounter such cold naturally. The coldest temperature ever recorded on our planet was minus 89.2 degrees Celsius at Vostok Station in Antarctica. This seems extremely cold to us, but compared to the Boomerang Nebula, this is almost tropical warmth. However, humanity has learned to create temperatures approaching absolute zero in laboratory conditions. In 2003, scientists from a Massachusetts Institute of Technology cooled sodium atoms to a temperature just a few billionths of a degree above absolute zero. But this requires complex equipment, laser cooling, and magnetic traps. Nature created the Boomerang Nebula without any technology. The Boomerang Nebula will not remain the coldest place forever. Over time, when the gas ejection slows down and radiation from the central star and the surrounding space begins to heat the nebula, its temperature will rise. According to scientists' forecasts, in a few thousand years, it will warm up to the temperature of the surrounding cosmic space. The study of the Boomerang Nebula helps us understand not only the physics of extremely low temperatures, but also the processes of stellar evolution. What is happening with the central star of the nebula also awaits our Sun in 5 to 7 billion years. When the Sun exhausts its fuel, it will also begin to shed its outer layers, creating a planetary nebula, although it will probably not be as cold. The shape of the Boomerang Nebula also arouses the curiosity of scientists. Its double structure, resembling butterfly wings, indicates that the ejection of matter did not occur uniformly in all directions. Perhaps the central star has a companion, where the star's magnetic field directed gas flows in certain directions, creating this unusual shape. Observations of the Boomerang Nebula show that it contains different temperature zones. The coldest regions are in the center of the nebula, where the gas has just been ejected and is expanding the fastest. As you move away from the center, the temperature gradually increases as the gas slows down and begins to interact with a warmer interstellar medium. In the composition of the Boomerang Nebula, astronomers have discovered not only simple molecules, but also quite complex chemical compounds. At such low temperatures, molecules practically have no energy for chemical reactions, so their presence indicates that they were formed in the star's atmosphere before the ejection or in the early stages of nebula formation. This gives us a unique opportunity to see the chemical composition of a dying star. The expansion speed of the Boomerang Nebula is truly impressive. If we could observe it in real time over several years, we would see it increase in size. Currently, its diameter is approximately 1 light-year, and it continues to grow. The gas shell moves outward, gradually dispersing into interstellar space. The central star of the Boomerang Nebula is currently in a transitional phase between a red giant and a white dwarf. It is still quite bright, but most of its mass has already been ejected into the surrounding space. In tens of thousands of years, this star will leave only a hot, dense white dwarf the size of approximately Earth, which will slowly cool over billions of years. Interestingly, the Boomerang Nebula is one of the few objects in space where the temperature is lower than the temperature of the cosmic microwave background. This means that it actually absorbs energy from the surrounding space rather than emitting it. In a sense, the Boomerang Nebula is a cosmic paradox. It is colder than the coldest environment in which it is located. Observations of the Boomerang Nebula in different ranges of the electromagnetic spectrum provide different information. In visible light, we see reflected light from the central star scattered by dust particles in the nebula. In the radio range, we can measure the temperature of the gas and determine its chemical composition. Infrared observations show the distribution of dust and the temperature of different zones of the nebula. One of the most interesting questions about the Boomerang Nebula is why exactly it is so cold, while other similar nebulae are not. Scientists suggest that the key factor is the extremely high speed of gas ejection. Most stars shed their shells much more slowly, which gives the gas time to heat up from the surrounding radiation. But in the Boomerang Nebula, the process occurs so quickly that cooling outpaces any possible heating. It is possible that the central star of the Boomerang Nebula is actually a binary system. Some astronomers believe that the presence of a companion star could explain both the unusual shape of the nebula and the extremely rapid ejection of matter. During the approach of two stars, mass transfer could occur, which accelerated the process of shedding the shell. The mass of matter in the Boomerang Nebula is enormous. The star has lost approximately the mass of our entire sun, and this matter now forms a cold cloud with a diameter of a light year. If we could collect all this gas and compress it back, we could create a new star, although it would be smaller than the original one, since part of the matter has already dispersed in space. Future of the central star in the Boomerang Nebula is predetermined. It will continue to lose mass until it becomes a white dwarf, a small, extremely dense object, where a teaspoon of matter would weigh several tons on Earth. This white dwarf will continue to radiate residual heat, gradually cooling over billions of years, until it becomes a theoretical black dwarf. Although the universe is still too young for black dwarfs to exist. The color of the Boomerang Nebula in images from Hubble shows us not only its shape, but also the distribution of matter and radiation. The bluish tint is the result of scattering of short-wave light on small dust particles, the same effect that makes our sky blue on Earth. Red regions may indicate of different chemical elements or warmer zones. Density of gas in the Boomerang Nebula varies from place to place. In some areas, the concentration of molecules is higher, creating denser clumps of matter. In other places, the gas is more rarefied. This unevenness tells us about the turbulent processes that occurred during the ejection of the shell and about the interaction of different layers of gas moving at different speeds. Magnetic field also plays a role in the Boomerang Nebula, although scientists are still investigating exactly how. Magnetic fields can direct flows of charged gas particles, creating channels and structures that we observe. This can also explain why the ejection occurred not spherically, but with a definite direction and shape. Radiation from the central star of the Boomerang Nebula not only tries to heat the surrounding gas, but also ionizes it, knocking electrons out of atoms. This creates a population of free electrons and ions that interact with the magnetic field and radiation in a complex way. These processes are similar to those occurring in more mature planetary nebulae, but in the Boomerang Nebula they occur in conditions of extreme cold. Studying such extreme objects as the Boomerang Nebula expands our understanding of the limits of the possible in nature. If we thought that the coldest place should be far from any stars in the depths of intergalactic space, nature showed us that the most extreme cold is created by the star itself during its death. This is a reminder that our intuition does not always work correctly on a cosmic scale. Comparison of the Boomerang Nebula with other planetary nebulae shows how diverse these objects can be. Some planetary nebulae are hot, with temperatures of tens of thousands of degrees. Others are cooler, but still warmer than the surrounding space. The Boomerang Nebula stands apart as a unique example of extremely rapid cooling and mass ejection. Impact of the Boomerang Nebula on our understanding of thermodynamics cannot be underestimated. It demonstrates that in open systems with rapid expansion, temperature can drop below the environment. This is not a violation of the laws of thermodynamics, but a demonstration of how these laws work in extreme conditions. Energy is not lost. It simply converts into the kinetic energy of expanding gas. Every second, the Boomerang Nebula ejects huge amounts of cold gas into space. If we could calculate how much energy is being expended in this process, the numbers would be astronomical. The star is expending the remnants of its energy to create this cosmic cold, and this process cannot last forever. It is a short-lived but impressive phenomenon on a cosmic scale. Question of how typical such objects as the Boomerang Nebula are remains open. Perhaps there are other, even colder nebulae that we haven't yet discovered. Or perhaps the Boomerang Nebula is a truly unique phenomenon, requiring a special combination of conditions. The mass of the star, the speed of ejection, the composition of the shell, to achieve such extreme cold. Role of heavy elements in the gas of the Boomerang Nebula is important for understanding the chemical evolution of the universe. These elements were created in the core of the star through nuclear reactions. Now they are returning to interstellar space, where they will mix with the primordial hydrogen and helium, enriching the material from which new stars and planets will form. When astronomers first discovered the Boomerang Nebula in 1980 using a ground-based telescope in Australia, they did not suspect how unique this object was. Initial observations showed only an unusual shape resembling a boomerang, hence the name. Only later detailed studies revealed the extremely low temperature of this nebula. Technological progress in astronomy has allowed us to see the Boomerang Nebula in unprecedented detail. The Hubble Space Telescope provided clear images in visible light, showing the complex structure of the nebula. The ALMA telescope, located high in the Chilean Andes, made it possible to measure temperature with an accuracy of a fraction of a degree. Infrared telescopes revealed the distribution of dust and organic molecules. In the Boomerang Nebula, processes occur that we can observe in laboratories on Earth, but on much smaller scales. Adiabatic expansion of gas is the basic principle of refrigerators, air conditioners, and many other cooling systems. Nature used the same principle, but on a cosmic scale, creating the largest natural refrigerator in the known universe. The impact of the Boomerang Nebula on the surrounding interstellar space also deserves attention. The gas and dust that are ejected enrich the interstellar medium with heavy elements. These elements will later become building material for new stars and planetary systems. In a sense, the death of one star gives life to future stars, planets, and perhaps civilizations. The cooling rate in the Boomerang Nebula is truly extreme. If you calculate, the gas loses heat at a rate that exceeds cooling in the most powerful terrestrial refrigeration units by billions of times. Of course, the volume of gas is also huge, but the very fact that natural processes can create such effective cooling is impressive. One of the mysteries of the Boomerang Nebula is how long it will remain so cold. Scientists predict that in a few thousand years, when the gas ejection stops and the nebula begins to disperse, the temperature will begin to rise. The cosmic microwave background, radiation from other stars, and even from the central white dwarf will gradually heat this gas to the usual cosmic temperature. Comparison of the size of the Boomerang Nebula with objects known to us helps to realize its scale. If we placed our solar system in the center of the Boomerang Nebula, it would extend far beyond the orbit of Pluto, covering a space thousands of times larger than our planetary system. And this entire huge region is filled with gas at a temperature of minus 272 degrees. The photons of light that we receive from the Boomerang Nebula carry the history of this object. Each photon interacted with atoms and molecules in the nebula, scattered on dust particles, and this interaction left a trace in the characteristics of light. By analyzing the emission spectrum, astronomers can determine not only the temperature and chemical composition, but also the speed of gas movement, density, and many other parameters. The molecular composition of the Boomerang Nebula tells us about the chemical processes that occurred in the star's atmosphere before the ejection. In addition to simple molecules such as hydrogen and helium, more complex compounds have been found there: carbon monoxide, cyanogen, formaldehyde, and other organic molecules. These substances were formed in the cold outer layers of the red giant, where the temperature was low enough for the formation of chemical bonds. The interaction of light with cold gas in the nebula creates unique optical effects. Some wavelengths are absorbed by molecules, creating dark lines in the spectrum. Others are scattered, giving the nebula a characteristic bluish tint. Each molecule has its own unique spectral fingerprint, which allows astronomers to accurately determine which substances are present in the nebula. Gravity still plays a role in the Boomerang Nebula, although insignificant. The central star attracts the surrounding gas, but the ejection speed is so high that gravity cannot hold this matter. The gas continues to move outward, gradually slowing down, but still leaving the stellar system forever. This is an irreversible process. The ejected matter will never return to the star. The Boomerang Nebula also demonstrates to us the limits of our understanding of physics. The behavior of matter at temperatures so close to absolute zero still contains many mysteries. Classical thermodynamics works somewhat differently under these extreme conditions, and quantum effects become more important. Studying such objects helps us refine our theories and better understand the fundamental laws of nature. The energy balance of the Boomerang Nebula is delicate.